Welcome, ladies and gentlemen, to 16.2, Part 1, which I've entitled the Electromagnetic Spectrum. I've got a picture here. I just did a Google image search for the electromagnetic spectrum. It's basically all electromagnetic waves, from the very, very long, which is radio, to the very, very short, which we call gamma rays. It's a spectrum. It's all of the waves that we just kind of blanket, and there's a certain smidge that we see, and we call that visible light. So here, this is the electromagnetic spectrum from the longest, which is radio, and then the next shortest is microwave, the next shortest is infrared, the next one is visible, and then ultraviolet, X-ray, and then gamma ray. All of these above what we can see, they're kind of harmful to us. Ultraviolet tans our skin. X-rays, they can damage you on a cellular level. Gamma rays also. You're only going to get gamma rays when you have nuclei fusing or fissioning. Stars, nuclear bombs give off gamma. Super harmful. On the other end, infrared, things below what we can see, infrared, microwave, and radio, those go on all the time. And they're present all around us, and they really don't do us any harm. And you can see the kind of relative scales. These pictures down here represent the scales of the wavelengths. Radio waves can be thousands of meters in length. Microwaves, which is basically the waves that your cell phones can use, microwaves inside of a microwave oven, they're on the scale of centimeters. You know, human beings would be in between there. Infrared, we're talking the head of a pin. Visible, we're getting down to like bacteria, and then on the size of nuclei. So I have a couple of videos that I wanted to watch, first of all, that talk about what are electromagnetic waves, and how big are they, and so on.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless. Yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is electromagnetic radiation? These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light.
Now, EM waves, this picture they've got going on here, if you remember back to when we played around with liquid nitrogen, how we moved electricity in a circle, and that electricity in a circle makes a magnetic field. And then if you have a magnetic field and you put a current-carrying device, that magnetic field makes electricity. And then because you have electricity moving in a circle, that makes a magnetic field. So electricity makes magnetic fields make electricity make magnetic fields. This is what an electromagnetic wave is that one disturbance in the magnetic field creates an electric field, which creates a magnetic field, and this propagation, this is what light actually is a jiggling, a changing in the electromagnetic field. And this picture that you see in front of you is an example. It's supposed to represent that. It's a poor representation because it's not really what light is. You know, what light truly is a really confusing thing that I don't think that we totally, as scientists, understand fully yet.
EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now.
And this is what Dr. Feynman had said. There's a huge mess all around you, but these things in front of your face, they sort it out. They sort out certain frequencies.
With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed.
And we'll talk about that more in subsequent lectures. Why do we see color? How do we mix? Like I mixed color in art class. How does that all work? That's where we're going next. Why does this leaf look green? Well, the short answer is because it absorbs everything but reflects green.
Waves interact with the chlorophyll molecules. Wave between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green.
So white light coming in, green is reflected.
And not tell us anything about how the leaf reflects ultraviolet, microwave, or infrared wave.
So there's all the waves strike that leaf. If it's infrared, who knows what it does to infrared? Does it absorb it? Does it reflect it? Absorption and reflection, that's all about what color is. And visibly, we know that it reflects green, but we can't tell does it reflect or absorb radio, infrared, ultraviolet, and so on. I've got a couple other cool videos here just to show you that how much of the light do we actually see,
Longest wavelengths. At the other end are gamma rays with the shortest.
I thought this was a really, really great
visible light,
visual for truly what do we actually see of the whole spectrum of light.
How small is the visible spectrum? If you had a reel of movie film representing the entire electromagnetic spectrum, stretching 2,500 miles from California to Alaska, the section containing the visible spectrum would fall somewhere in the middle, near the University of Washington.
This frame is the whole visible spectrum. It is one frame and over 2,000 miles of tape.
Isn't that nuts? That 2,500 miles and these things in front of your eyes only pick up 1 inch of it. Like that, there's so much going on in the universe that we don't see. But it's just so amazing to look around and just the amazing things that you can see, but it only represents 1 inch of 2,500 miles worth of information. It just boggles my mind what else is truly out there. And it would be really cool to see what else is out there in different spectrums. And we actually do that. When astronomers look at the sun, this is what we see. When we look at the sun in visible light, that's what we see. You see these little dark spots on there. Those are called sunspots. But what happens when you look at it in ultraviolet light, or you look at it in X-ray, or you look at it in gamma rays? Well, gamma rays, this is a very pixelated image because of the detectors that they're using. But what if you look at it in heat, infrared, or in radio? It's really neat to look at things in different spectrums to see what's truly there. And we look at it in, let's say, X-ray, but we convert that into a visible signature. So we call white really high X-ray values, and we call black really low X-ray, and we these are false colored images. This is not truly what it looks like, but we've assigned a color to an ultraviolet value. For instance, and this is the United States frequency allocate. This is for the radio spectrum. If you look down here, this is the radio spectrum of things, and these are all the frequencies, and it's just nuts. Like, for instance, AM broadcasting goes from 535 up to 1600, 17, and then you get some other stuff going on in here. But these are all, I got this from Wikipedia. This is just a chart that shows you certain frequencies are bought by different companies like Verizon, US Cellular, AT&T. They buy certain bandwidths. Government agencies, aeronautical radio navigation, they have all these have specific TV channels, 7 through 13. They all have different allocations inside this bandwidth. Absolutely incredible. The last one, I wanted to show you just two more real quick ones. Maybe you've seen this one. This is, what do people look like in ultraviolet? Like what they did, they used a camera. Here's a person. What do they look like in the UV spectrum? And you can see the freckles just come out. A person with freckles, the reason that you see those freckles is because the ultraviolet light hitting them, some of that ultraviolet light is absorbed. That's why it looks black, is because it's absorbing some of the ultraviolet light, and then it looks white because it's reflecting ultraviolet light. So when we look at it through a UV filter, you see that these freckles come up because some of the face is absorbing the UV, some of it is reflecting the UV, and the camera's picking up that absorption versus reflection. And you get to see really what's going on there.
What you see is what you get. And worse yet, I can give an explanation for why it's gray on your side. Better yet, I'll give you an indication for why you're feeling deprived.
An interesting thought would be, I wonder what sunscreen does, because sunscreen is supposed to protect you from the sun. So what would you look, if you put sunscreen on your face and then looked into a UV, what would that look like? And then this one right here, maybe you've seen before. This is a thermal camera. This is what the world looks like in heat. So what it's doing is it's assigning temperatures to specific colors. And I think they show the color scale. Yeah, red means hot, blue means cold, white means especially hot. So sunscreen, that's looking at it in heat now, not UV. Laptop on a person's lap, curling your hair. Now this is interesting. It can't see through glass. Heat, visible light transmits through glass, but heat reflects off it. And that's an interesting thing. Why does some light travel through objects, and like radio waves can go right through a building, but visible light doesn't. Visible light can go right through glass. Heat doesn't. What makes an object see-through and it not see-through? Again, glass is physically see-through it. Heat does not transmit through it. You can see the coils from the compressor. The convection currents that you can see, the convection cells, these are called. Here you can start to see the vasculature underneath the skin from someone who's exercising. Now I've always wanted to get one of these cameras, but they're like 20 grand at the time that I made this video. It does reflect in a mirror, so that's interesting. Visible light and infrared will both reflect off a mirror. This video right here, it's a NOVA special. It's 2 hours long, but it talks about all the different satellites we have up in space that look at Earth in different wavelengths to figure out what's going on. And it shows how Earth is a true system, how dust storms in the Sahara affect the rainforests in Brazil, and it's just incredible. And how that affects. It's just incredible how everything works together. How you think that we're separate pieces, but it's a unique system. So the electromagnetic spectrum, I just wanted to introduce you to it today to show you its constituents from the very large wavelength radio, microwave, infrared, visible, ultraviolet, X-ray, and all the way up to the highest energy gamma rays.